Sometimes I look up at the night sky and feel this profound sense of smallness against the backdrop of cosmic time.
Uh-huh.
But then I think about our own planet's history, this immense, almost unfathomable expanse, and I get that same feeling, but it's also deeply captivating. It makes you wonder how we even begin to grasp something so vast.
That very challenge of comprehending Earth's immense history is exactly what we're diving into today.
Right.
Our source is the chapter Deep Time, How Old is Old, which basically gives us the geologist's toolkit for understanding our planet's timeline.
Yeah.
Kind of like how John Wesley Powell's exploration of the Grand Canyon revealed these previously unimaginable depths of geological history.
Exactly. Imagine Powell and his crew navigating that colossal chasm.
Yeah.
Each layer of rock they saw was like a tangible record of eons past. And that's our mission today, to make sense of this deep history. We're going to explore how geologists piece together Earth's autobiography, from figuring out the order of events, relative dating, for putting actual dates on those events in years, numerical dating.
Yeah.
We want to make this grand story accessible and, frankly, as fascinating as it truly is.
And as we explore this chapter, you'll see how these fundamental geological ideas aren't just like abstract concepts. They connect directly to spectacular places like the Grand Canyon and the unique rock formations of southern Utah. We'll be unraveling concepts like relative age, the crucial role of unconformities.
Those gaps.
Yeah, those gaps in the timeline that force us to be geological detectives, how we link rock layers across vast distances, and finally, how radiometric dating gives us those crucial numerical ages. It's about understanding not just what happened, but critically, how we know.
Okay, let's start by unpacking how our understanding of Earth's age even began to shift. Because for the longest time, the prevailing idea was that Earth was relatively young, right? Closely tied to human history. I mean, we even had Archbishop Usher in the 17th century pinpointing Earth's creation to a very specific date.
That's right. Usher's calculation, putting Earth's origin around 4004 BCE, reflected a very human-centered timescale. What's fascinating is how the seeds of a much deeper understanding were sown through just, careful observation. Nicholas Steno, an Italian physician, made a pivotal contribution here.
Ah, yes, the tungstones. Tell us that story.
Right. So Steno noticed these peculiar triangular rocks, known back then as tungstones.
Yeah.
And he saw they bore this striking resemblance to the teeth of sharks. But his insight went beyond just, these look similar.
Right.
He proposed that these tungstones were actual shark teeth buried in sediments that later solidified into rock and were then somehow uplifted to form mountains.
Wow.
And this seemingly simple observation had really profound implications. It suggested the Earth is dynamic, it changes over time, and that rocks themselves hold actual evidence of past life.
So from mythical dragon tongues to tangible shark teeth, that's a monumental leap in understanding.
It really was.
And then we have James Hutton, the Scottish geologist. He's often considered the father of modern geology, isn't he?
Indeed. Hutton, living during the Enlightenment, he really championed natural explanations for the geological features he observed. While exploring the Scottish Highlands, he noticed parallels between patterns in ancient sedimentary rocks, like ripple marks, and those forming in contemporary environments. Today, this led him to articulate the principle of uniformitarianism.
The present is the key to the past.
Yeah.
I find that so powerful. So the everyday processes we see in action today, erosion, deposition, volcanic activity, these very same forces, just operating over immense timescales, are what sculpted the Earth we see now.
Exactly. It completely reframes how you look at a flowing river or a crumbling cliff face.
Yeah.
And because these processes generally occur at a slow rate, Hutton recognized that vast stretches of time must have been necessary to create the geological features he studied.
Right.
He famously stated that he could find no vestige of a beginning nor prospect of an end, which is just a testament to his perception of Earth's immense age.
This sets the stage perfectly for understanding the difference between relative and numerical age.
Yeah.
Right? First, we figure out the sequence, like a historical timeline.
Yeah.
We might know the Renaissance happened before the Industrial Revolution. That's relative order.
Right.
But knowing the actual century those periods occurred in, that's numerical age.
Precisely. Relative age gives us the what came before what, while numerical age provides the when in actual years using those abbreviations like Ka for thousands, Ma for millions, and Ga for billions of years ago. And geologists were able to establish relative ages long before we had the technology for numerical dating.
Okay. And that leads us to Charles Lyell, who really formalized these foundational ideas into a clear set of principles that geologists still use today to determine relative ages.
Yeah, through his hugely influential book, Principles of Geology, Lyell meticulously laid out these fundamental concepts. First, uniformitarianism, which we've just talked about.
Yep.
Then, the principle of original horizontality. This just states that sediments are initially deposited in horizontal layers. Gravity pulls them flat.
Makes perfect sense.
So if we observe rock layers that are tilted or folded, that deformation must have happened after the layers were originally laid down.
Right, after they were flat. Got it.
Exactly. Next is the principle of superposition. In any undisturbed sequence of sedimentary rock layers, the oldest layers will be at the bottom and the youngest at the top.
Like stacking books.
Exactly like stacking books, the first one you put down is at the bottom. Simple, but powerful.
Another one that feels intuitively right. What comes next?
The principle of lateral continuity. This tells us that sediments generally accumulate in continuous sheets across a region.
Okay.
So if we see a layer of rock that's been divided by, say, a canyon, we can infer that it was once a continuous layer across the whole area where the canyon now exists before the river carved its path.
Like that layer just kept going before the erosion happened. Got it.
Exactly. Then we have the principle of cross-cutting relations. If one geologic feature cuts across another, the feature that is cut is older than the one that cuts it.
Okay, so the cutter is younger.
Right. This applies to features like igneous dikes slicing through sedimentary beds or faults displacing rock layers. The thing doing the cutting is the younger event. So a dike slicing through rock layers is younger than those layers it cuts.
Got it. And what about inclusions? These little bits inside rocks.
Right, the principle of inclusions. This states that a fragment of one type of rock found embedded within another rock type must be older than the rock that contains it.
Okay.
For instance, if a younger sandstone layer contains pebbles of an older granite, those granite pebbles had to exist before the new sand was deposited around them.
Makes sense.
And this is particularly helpful in distinguishing between something like a sill and a lava flow. A sill, which is magma intruding between existing layers, might contain fragments, inclusions of the surrounding rock it squeezed through. A lava flow, solidifying on the Earth's surface, might later be buried by sediment containing fragments eroded from that solidified flow after it cooled.
Ah, that's a clever way to differentiate them. And finally, baked contact.
Yeah, the principle of baked contacts tells us that if an igneous intrusion heats up and alters or bakes the surrounding rocks, then those baked rocks must be older than the intrusion that heated them.
Okay.
You often see a finer-grained, chilled margin along the edges of the intrusion, where it cooled rapidly against the cooler surrounding rock. Like pouring hot fudge onto cold ice cream, the edge chills fast.
Right.
That little detail helps us understand the order of events.
So these principles give us this powerful toolkit for figuring out the sequence in which geological events happened. And the chapter provides a fantastic example, that figure 12.5.
Yeah, that's a good one.
Showing a sequence of sedimentary beds, a sill, folding, a pluton, a fault, a dike, and then erosion. It walks you through, step by step, how to apply all these rules to reconstruct the order. It's like being a geological detective.
It truly is. You start by identifying the oldest layers using superposition, then you look for cross-cutting relationships to place intrusions and faults, and finally, you consider erosion, which always affects the older features first.
And then we move on to fossils. William Smith, during his work surveying canals,
Right, Stratismith.
he made the crucial observation that different layers of rock contain distinct and recognizable groups of fossils.
Precisely. Smith observed that these fossil assemblages, the specific collections of fossil species, were unique to certain intervals of rock strata. And importantly, once a fossil species disappeared from the sequence, it never reappeared in the higher, younger layers.
Never came back.
This led to the principle of fossil succession. Fossil organisms succeed one another in a definite and predictable order. Any period of geologic time can be recognized by its fossil content. Essentially, extinction is forever.
So we can use fossils as time indicators to figure out relative ages. If one layer has fossil A and a layer above it has fossil B, we know the layer with B is younger, assuming B evolved after A.
Exactly, and certain fossils, known as index fossils, are particularly valuable. They were geographically widespread, but existed for only a relatively short period of geologic time.
So they pinpoint time well.
Exactly. Finding an index fossil in a rock layer can help pinpoint its age quite precisely relative to other rock layers around the world. Figure 12.7 shows this really well, how different fossil species have limited lifespans within a rock sequence, and how those ranges overlap, creating a predictable succession. And, this understanding of fossil succession is also fundamental support for the theory of evolution.
Absolutely. So we've got these amazing tools for putting events in chronological order. But what about the gaps in the record? The chapter discusses unconformities. These are like missing chapters in Earth's history book, aren't they?
That's a perfect analogy. An unconformity represents a break in the geologic record, a surface where deposition stopped and erosion might have even removed previously formed rocks before new layers were laid down. James Hutton himself was the first to really grasp the significance of these breaks when he visited Sycamore Point in Scotland.
What did he see there that was so groundbreaking?
At Sycamore Point, Hutton observed this really dramatic angular unconformity. He saw nearly vertical layers of older gray rock lying beneath gently dipping layers of younger red rock.
Quite a contrast.
A huge contrast. He realized that the lower layers must have undergone this significant history. Deposition, getting turned into rock, tilted almost vertically, eroded down substantially, and then the upper layers were deposited on top of that eroded surface.
Wow.
The boundary between these two sets of rocks represented a vast amount of time that wasn't recorded by continuous sedimentation, a huge gap.
So deposition, then massive tectonic upheaval and erosion, and then much later more deposition. That's a huge amount of missing time.
Precisely. The period of missing time represented by an unconformity is called a hiatus. Geologists recognize three main types of unconformities. The first, like at Sycamore Point, is the angular unconformity.
Tilted layers below, flat ones above.
Exactly. Tilted or folded layers below an erosional surface, and horizontal or gently dipping layers above, clearly indicates a period of deformation before the newer layers were deposited.
Okay, and the other types?
Next, we have the nonconformity. This is where sedimentary rocks lie directly on top of much older, intrusive igneous or metamorphic rocks, the crystalline basement rocks.
Right, like sandstone on granite.
Exactly. This implies that the older crystalline rocks were uplifted, exposed at the surface, eroded, and then subsequently buried by new sediment that eventually became sedimentary rock. The contact represents a significant, often very lengthy time gap.
Got it. And the last type?
Finally, there are disconformities. These can be the trickiest to spot because the rock layers above and below the unconformity are parallel.
Ah, okay.
A disconformity represents a period of erosion or non-deposition within a sequence of otherwise continuous and parallel sedimentary layers. Fluctuations in sea level are a common cause.
So things look parallel, but time is missing.
Exactly. You might have deposition in a shallow sea, then sea level drops, causing erosion, then sea level rises again, and new deposition happens on that eroded surface. The time gap might be subtle, revealed maybe by a break in the fossil record, or an actual visible erosion surface, maybe a layer of pebbles concentrated at the boundary, or even a paleosol, an ancient buried soil layer. Fench 12.10 shows one with a paleosol.
So unconformities are a reminder that no single location on Earth holds a complete, uninterrupted record of all of geologic time.
Absolutely not.
It's like our history book has pages torn out everywhere, which makes you wonder about places like the Grand Canyon. Does it show us the entire history of the Earth?
That's a very insightful question, and the answer is no. While the Grand Canyon exposes a remarkably thick and diverse sequence spanning vast amounts of time, it definitely contains unconformities. Even in a place as geologically spectacular as the Grand Canyon, there are significant gaps in the record, representing periods of time for which we don't have continuous rock deposition preserved in that specific location.
Okay, so we have these fragmented records. How do geologists piece them together to get a more comprehensive understanding of Earth's history? That's where stratigraphic formations and correlation come in, right?
Exactly. William Smith, back during his canal work, noticed that certain distinctive sets of rock layers, characterized by specific rock types and fossils, appeared repeatedly in different places.
Recognizable units.
Yes, these recognizable and mappable units are what we now call stratigraphic formations. A formation is basically a body of rock of a specific type or a consistent group of rock types that can be traced over a reasonably large area. It represents sediment accumulation during a specific time interval. The boundaries between formations are geologic contexts.
And to visually organize these formations at a particular location, we use stratigraphic columns, like geological profiles.
Yes, stratigraphic columns are usually drawn to scale, showing the relative thicknesses of the formations at a given spot. They might show rock types, maybe resistance to erosion. And crucially, unconformities are usually marked with a distinctive wavy line on these columns. Figure 12.11 shows the famous Grand Canyon stratigraphic column.
Right. And then to build a broader picture, we need to connect these columns from different places. That stratigraphic correlation, how's that done?
Geologists use two main approaches. First is lithologic correlation, looking for similarities in rock type and sequence between locations.
So matching the rocks themselves.
Right. If you see the same distinctive sequence, sandstone, shale, limestone, in two nearby areas, you can reasonably infer they formed around the same time. Sometimes there's a really distinctive layer, a marker bed or key bed, maybe a volcanic ash layer, that's easy to spot over a wide area and makes correlation much simpler.
Like connecting the dots between nearby cliffs.
Yeah, the rocks on the north and south rims of the Grand Canyon, for instance, can be correlated largely through lithologic similarities.
That makes sense. If it looks the same nearby, it's probably the same stuff from the same time. But what about correlating strata over much wider distances? Or when the rock types themselves are quite different?
That's where the power of fossil correlation comes in. This method compares the fossil assemblages found within different rock layers, even if the rock types themselves aren't the same.
Ah, using the fossils again.
Exactly. You might have sandstone in one region and limestone in another, but if they contain fossils of the same relative age, especially those index fossils, we can correlate them. They formed during the same general time period.
Okay.
Fossil correlation is super valuable for correlating strata across continents or between different latitudes, where environments, and thus sediment types, might have been very different at the same time. Figure 12.12 illustrates this really well.
So even if one place was a desert and another was a shallow sea, the fossils can tell us if they existed at the same time.
Precise.
And the chapter gives that great example of correlating strata between the Grand Canyon and Las Vegas, showing how the Monte Cristo limestone near Vegas correlates in age with the Redwall limestone in the canyon based on fossils, even though they have different thicknesses and maybe some missing layers in one or the other.
Exactly. That example highlights how geologic history can vary regionally, maybe due to differences in subsidence rates between a basin and the more stable continental craton.
And this growing understanding of how rock layers are distributed geographically led William Smith to create the first modern geologic map. So it's not just the vertical sequence, but the spatial arrangement across the surface.
Precisely. Geologic maps use different colors and symbols to show where different rock units are exposed at the Earth's surface. And the patterns of these colors and symbols can reveal underlying structures, folds, faults, unconformities. For instance, an anticline, an upward arching fold, often shows the oldest rocks exposed in the center on a map, with younger rocks flanking it. Modern maps often use digital elevation data too, and are usually paired with cross-sections showing the interpreted geology underground, like in figure 12.14.
So by carefully piecing together all these local stratigraphic columns and then correlating them with columns from literally all over the globe,
Millions of locations.
geologists have been able to construct the geologic column, this ultimate composite representation of Earth's entire history.
Yes, the geologic column, shown in figure 12.15, represents the entirety of Earth's history, assembled from countless studies worldwide. But it's crucial, like you said, to remember no single place has this whole record.
It's a compilation.
It's a masterful synthesis, a global framework built by correlating rocks and fossils from everywhere.
And this vast column of time is then divided into these major chunks, eons, eras, periods, and epochs. You can feel a bit like learning a whole new calendar system.
It can indeed. The biggest divisions are the eons: Hadean, Archean, Proterozoic, and Phanerozoic. The first three are often just lumped together as the Precambrian.
Okay.
The Phanerozoic eon, meaning visible life, is what most people think of with abundant fossils. The Proterozoic means earlier life, though we now know life started even earlier in the Archean. Eons are split into eras: Paleozoic, ancient life; Mesozoic, middle life; and Cenozoic, recent life, all within the Phanerozoic.
And then periods and epochs.
Right. Eras are divided into periods and periods into epochs. The names often relate to geography, like the Jurassic period named after the Jura Mountains, or characteristics like the Carboniferous for its coal.
Yeah.
What's important to remember is that these divisions were initially set up based on major changes seen in the fossil record, big evolutionary events.
Not based on equal time chunks.
Not at all. Because the timing of these biological changes varied, the divisions don't represent equal spans of time. We didn't know the actual durations until numerical dating came along.
And the geologic column gives us this incredible overview of how life on Earth has evolved,
Mm.
as shown in figure 12.1 Steen, from the earliest single cells in the Archean
Bacteria and archaea.
to shelled invertebrates late in the Proterozoic, then the Cambrian explosion, then fish, land plants, amphibians, reptiles, dinosaurs, mammals, birds.
Yeah, the fossil record in the column tells that grand story. Key events like the Cambrian explosion around 530 million years ago, the Mesozoic age of reptiles, the Cenozoic age of mammals, they all fit into this timeline.
And we can then use this standardized geologic column to correlate rocks across huge regions, like the Colorado Plateau example,
Right, Arizona and Utah.
where the Grand Canyon shows older rocks at the bottom, and as you go north through Zion and Bryce Canyon, you hit progressively younger rocks.
Exactly. Each of those iconic parks represents different time intervals and past environments, all fitting together within the big picture of the geologic column, as figure 12.1 illustrates. It gives us a coherent picture of the past.
Okay, so we've established how geologists determine the relative order of events, super important, but how do we actually assign those crucial numerical ages, those dates and years? That's where the magic of radioactivity comes in, right?
Exactly. While relative dating gives us the sequence, it wasn't until the discovery of radioactivity that geologists could determine the absolute or numerical age of rocks, their age in years. This field, geochronology, mostly relies on isotopic dating, also called radiometric dating.
And it revolutionized everything.
Completely. It allowed us to put actual numbers on the vast expanse of deep time.
So what's the fundamental principle? How does radioactive dating actually work?
Okay, so certain elements exist in unstable forms called radioactive isotopes. These isotopes spontaneously undergo a process called radioactive decay, where they transform into atoms of a different element or maybe a more stable isotope of the same element.
Okay.
And this decay happens at a predictable, measurable rate. The original radioactive isotope is the parent isotope, and the stable one it decays into is the daughter isotope.
And the rate is quantified by the half-life.
Yes. The half-life of a radioactive isotope is the time it takes for 1/2 of the parent atoms in a sample to decay into daughter atoms.
Okay.
And crucially, the half-life is constant for any given isotope. It's not affected by temperature, pressure, chemical reactions, nothing. Figure 12.19 has that helpful visual analogy.
Right, like starting with 100 parent atoms.
Yeah. After one half-life, you have 50 parent and 50 daughter. After another half-life, you have 25 parent and 75 daughter. Half of the remaining parents decay each time.
So the parent decreases exponentially, daughter increases.
Exactly. So by carefully measuring the ratio of parent to daughter isotopes within a rock sample and knowing the precise half-life of the parent isotope, we can calculate how many half-lives have passed since the radioactive clock started ticking in that mineral, and therefore determine its age.
So measure the ratio, know the half-life, calculate the time. Sounds straightforward, but I bet the process is tricky.
Oh, it's meticulous. First, you collect fresh, unweathered rock samples. Weathering can mess up the ratios.
Right.
Then, in the lab, you separate out specific minerals known to contain suitable radioactive isotopes. Think zircon, potassium feldspar, things like that.
Okay.
Then, you chemically extract the parent and daughter isotopes from these minerals, often using strong acids or lasers, all in ultra-clean labs to avoid contamination.
High-tech stuff.
Very. Finally, you analyze the precise amounts of parent and daughter isotopes using a highly sensitive instrument called a mass spectrometer. It separates and measures isotopes based on their mass, as shown in figure 12.2.
And this measured ratio tells us how many half-lives have gone by since the clock started. But when did the clock actually start?
That's a key point.
Mm-hmm.
The radioactive clock doesn't really start ticking until the mineral cools below a specific temperature, its closure temperature or blocking temperature.
Closure temperature, okay.
Above that temperature, atoms can diffuse in and out of the crystal lattice. Parent or daughter isotopes can escape or move around.
So the system isn't closed.
Exactly. Once the mineral cools below its closure temperature, the atoms get locked in place. From that point on, the parent-daughter ratio accurately reflects the time since cooling. So for igneous rocks, isotopic dating generally tells us when the mineral crystallized and cooled from magma or lava. For metamorphic rocks, it typically dates when the rock cooled down after metamorphism.
Okay, that's an important distinction.
And there's even a field called thermochronology that uses isotopes with very low closure temperatures to date when rocks were uplifted and eroded back towards the surface.
Fascinating. So we're often dating the cooling, not necessarily the exact moment of formation.
Yeah.
What about sedimentary rocks? Can we directly date sandstone or shale this way?
Not usually, no. If you date individual mineral grains within a clastic sedimentary rock, like sand grains in sandstone,
Yeah.
you're typically dating when those grains originally crystallized in their source rock, the igneous or metamorphic rock they eroded from, not when the sediment itself was deposited.
Right, you're dating the ingredients, not the cake.
Exactly. However, there's a technique called detrital geochronology, where you date lots of individual grains. It tells you the ages of the source rocks, and the age of the youngest grain gives you a maximum age for the sedimentary rock. The sediment has to be younger than the youngest grain it contains.
Okay, so that sets a limit. But for precise age of the sedimentary rock itself, we often need indirect methods.
Exactly. We often date associated igneous or metamorphic rocks that have a clear relationship with the sedimentary layers. Like, if a sedimentary layer sits unconformably on a granite that we date, the sediment must be younger than the granite. Or if a dated basalt dike cuts through sedimentary rocks, the sediments must be older than the dike.
Okay.
Volcanic ash layers interbedded within sedimentary sequences are also incredibly useful because the ash itself can often be dated radiometrically, giving a direct age constraint for the sediments right above and below it. Figure 12.24 shows this principle, bracketing the age of a Cretaceous sandstone with dinosaur fossils between a dated granite below and a dated basalt dike cutting through above.
So you box it in, age-wise.
Precisely. And by applying these techniques worldwide, especially where rocks have clear relationships to the geologic column divisions, geologists have assigned numerical ages to the boundaries between periods and eras. That gives us the detailed, calibrated geologic timescale we use today, like in figure 12.25.
And it's always being refined, right, as we get better data.
Absolutely. It's a dynamic scientific construct. The age of the Cambrian-Precambrian boundary, for example, has been refined as more precise dates came in. And every reported numerical age always has an uncertainty value, reflecting the analytical precision.
And finally, the biggest question of all, how old is the Earth itself? I remember reading about Lord Kelvin's attempt to calculate this back in the 19th century. He was way off, wasn't he?
He was. Lord Kelvin, a brilliant physicist, tried to estimate Earth's age based on how long it would take an initially molten Earth to cool down. His calculations gave maybe 20 to 100 million years.
Which we now know is far too young.
Way too young. The huge flaw was that he didn't know about radioactivity, the immense heat generated inside the Earth by the decay of elements like uranium, thorium, potassium. This internal heat source dramatically slows down the cooling.
So the very phenomenon Kelvin was unaware of, radioactivity, not only messed up his calculation, but also gave us the tool to find the real age. Kind of ironic.
It is pretty ironic. So by isotopically dating the oldest known crustal rocks on Earth, about 4.03 billion years old, found in places like northwestern Canada.
Wow.
And dating rocks from the moon, some around 4.5 billion years old.
Wow.
And especially by dating various types of meteorites, which consistently yield ages around 4.56 to 4.57 billion years.
Meteorites, why them?
Because meteorites are considered basically unchanged leftovers from the formation of the solar system. They haven't been through the intense geological recycling that Earth and even the moon have experienced, so they give us the most reliable estimate for the age of the solar system and thus the Earth.
So the Earth formed around 4.56 billion years ago.
That's the accepted age. The reason we don't find many Earth rocks older than about 4 billion years is likely due to the intense heat and constant meteorite bombardment during the early Hadean eon, which would have melted and reworked the earliest crust.
4.56 billion years. That is just an almost incomprehensible span of time.
It really is.
The chapter uses some really effective analogies to help us wrap our heads around it, like comparing Earth's history to the height of the Empire State Building.
Right. Figure 12.27.
Where all of human history is just a thin layer of paint at the very top, or compressing all 4.56 billion years into a single calendar year.
Right, the calendar year analogy. Oldest rocks in February, Cambrian explosion late October, dinosaurs mid-December.
And all of recorded human history happens in the last minute or two before midnight on December 31st.
Those kinds of analogies are incredibly useful. They really drive home the sheer magnitude of deep time and just how recent we are in the grand scheme of things.
It truly is mind-boggling. So just to recap, we've journeyed through understanding the crucial difference between relative and numerical age dating.
Yeah.
The fundamental principles geologists use to figure out the order of past events.
Yeah.
The significance of unconformities as these unavoidable gaps in the record.
Right.
The methods of stratigraphic correlation used to build the big picture geologic column. the principles and application of radiometric dating for putting actual numbers on things.
The numerical ages.
And finally, how all this evidence converges to give us our understanding of the geologic timescale and the staggering 4.56 billion year age of our planet.
That's an excellent summary. We've really hit the core concepts from the chapter, the main ideas, key processes like superposition and radioactive decay. And we touched on the kinds of examples you'd explore in those geotours sections, like looking at relative dating and unconformities in southern Utah, or the formations and monoclines in Circle Cliffs. We've tried to explain terms like uniformitarianism, half-life, closure temperature plainly, and connect them to real places like the Grand Canyon and the Colorado Plateau.
It truly changes your perspective, doesn't it? To really contemplate the billions of years of dynamic change that have shaped the very ground beneath our feet. It's not static at all.
It absolutely does. And it kind of leaves us with a profound question, doesn't it? Considering this immense timescale we've discussed,
Yeah.
what future transformations might our planet and the life it supports undergo that are currently just beyond our ability to even imagine? Think about the vast cycles of geological and biological change over billions of years. What incredible new chapters of Earth's story are yet to be written.
Wow. A truly thought-provoking note to end on. It certainly makes you wonder about the long-term future and what stories the rocks of eons to come will tell about our time. Well, that's all the time we have for this deep dive. Thanks so much for joining us.
It was a pleasure. Always fascinating to talk about deep time.